Good morning, everyone. I'm Dipanshi from BSc Chemistry Honors third year. Hard and soft acids and bases. The terms acids and bases are routinely used in our daily life. Chemists have been classifying substances as acids and bases since long time. Lavoisier noted that the common element in all acids was oxygen. The word oxygen in Greek means acid former. However, Humphrey Davy showed later that all acids contain hydrogen. It was in 1884 Arrhenius, a Swedish chemist, developed the theory of acids and bases known today popularly as Arrhenius theory of acids and bases. According to Arrhenius, an acid is a substance which gives hydrogen ions H positive in aqueous solution, and a base is a substance which gives hydroxyl ions in aqueous solution OH negative. The strength of an acid or a base depends upon its capacity to provide H positive and OH negative ions respectively. The process of neutralization of an acid by an base can be represented by the reaction H positive plus OH negative gives H2O. In 1923, J. N. Bronsted in Denmark and T. M. Lowry independently proposed a new acid base theory. According to their theory, an acid is a proton donor, whereas a base is a proton acceptor. The acid base reaction is regarded as proton transfer reaction. In 1923, G. N. Laffitte gave another general definition of acid base behavior in terms of electron pair donation and acceptance. However, this theory got the recognition only in 1938. According to Lewis, an acid is a substance which can accept a pair of electrons, while a base is a substance which can donate a pair of electrons. In other words, an acid is an electron pair acceptor, while base is an electron pair donor. The earlier definition of acids and bases were solely based upon the observable properties such as taste, ability to dissolve substance insoluble in water, their effect on vegetable dyes. The term acid was applied to substances that have a sharp or sour taste, turns blue litmus red, react with certain metal to liberate hydrogen gas and have the ability to dissolve substances insoluble in water. On the other hand, the term base was applied to substances that have a bitter taste, soapy feel, turn red litmus blue. However, tasting and feeling chemicals are dangerous method of determining whether the substance is an acid or base. You should never ever taste or touch solution of chemicals in laboratory. There are, however, other methods of recognizing acids and base. For example, acids and base change the color of certain dyes, popularly known as indicator. One of the most common indicator is a vegetable dye obtained from known as litmus. Aqueous solution of acids turn the litmus red, whereas aqueous solution of bases turn it blue. Thus, any substance which has an unshared pair of electron can act as a Lewis base, whereas a substance which has an empty orbital to accommodate a pair of electrons act as Lewis acid. In other words, capable of donating a pair of electrons are regarded as Lewis base, and substances capable of accepting a pair of electrons are regarded as Lewis acid. Acid-base neutralization reaction may thus be regarded as donor, Lewis-base acceptor, Lewis acid reaction, or coordinate covalent bond formation reaction. The classical example of Lewis acid-base reaction is that of between boron trifluoride and ammonia. Using electron dot diagram, we can see that boron trifluoride is a Lewis acid and ammonia is a Lewis base. NH3 plus BF3, H3N gives BF3 donor receptor coordinate bond formation reaction. Lewis concept of acids and bases is very commonly used, and because of its simplicity and ease with the formation of coordination compounds can be explained. In brief, all the usable ligands can be regarded as Lewis base, all the metal ions can be regarded as Lewis acid. The degree of affinity of a metal ion for ligands can be termed Lewis acidity, and tendency of the ligand to combine with metal ion can be regarded as Lewis basicity. Hard and soft acids and bases. An acid-base reaction, according to Lewis concept, involves a reaction between a donor and an acceptor to form complex. A plus B gives AB, or B donates to A. The formation of the stable complex between donor A and receptor B depend on the nature of species A and B involved. It has been known since long that certain ligands form stable complexes with metal ions such as Ag positive, Ag2 positive, Pd2 positive, and Pt2 positive. On the other hand, certain ligands Form stable complexes with metal ions such as Al3 positive, CO3 and PT4. Based upon the preferential bonding, the acid and bases have classified into two groups, Class A and Class B, according to their preference. Class A metal ions include metal, alkaline earth metal, light and more highly charged ions, Ti4 positive, Cr3 positive, Al3 positive, Fe3 positive, CO3 positive, etc. Hydrogen ion. Class B metal ions include heavier transition metals second and third series with Cd2 positive, Hg2 positive, Pd2 positive, Pt2 positive. Heavier transition metal in lower oxidation state, Ag positive, Hg2 positive, Cu positive. Low valent metal ions such as zero valent metals in metal carbonyls. Class A ligands include molecules or ions with donor atoms NOFCl. It is important to know that Class A ligands prefer to form strong complexes with Class A metals. Class B ligands include molecules with donor atom P, AS, S, SEI, etc. Class B ligands prefer to form complexes with Class B metal ions. It was in 1963 Pearson coined the term hard and soft acid bases for Class and Class B metal ions and ligands respectively. Accordingly, Class A metal ions are referred to as hard acids. Class B metal ions are referred as soft acids. Similarly, Class A ligands are named as hard bases, whereas Class B ligands are termed as soft bases. In summary, according to Pearson, Class A acids are hard, H positive, Li positive, Na positive, Be2 positive, Mg2 positive, Cr3 positive, Fe3 positive. Class B acids are soft acid, Ag positive, Pd2 positive, Cu positive, Pt2 positive. Class A are hard bases, H2O, NH3, F negative, ROH. Class B soft base, R3P, R3S, R2S, R2SE, I negative, SCN negative, etc. Classification of acids and bases as hard and soft. Pearson observed that it is possible to correlate acid-base interactions as the bases of hard and soft acid and bases. He observed that type metal ions acids were small, compact and not very polarizable. These preferred ligands that were also small and less polarizable. He called these acids and bases as hard. On the other hand, the type B metal ions and ligands they prefer appear to be larger in size, more polarizable. He described these acids and bases as soft. Pearson generalized the acid-base relationship and expressed that hard acids prefer hard base and soft acids prefer soft bases. Classification of acids. A general classification of some common hard and soft acids along with some borderline cases is given in table 4.1. Hard acids: H positive, Li positive, Na positive, K positive, Be2 positive, Mg2 positive, Ca2 positive, Cr2 positive, Al3 positive, Sc3 positive, Ga3 positive, Ln 3 positive, La3 positive, Cr3 positive, CO3 positive, Fe3 positive, As3 positive, Ce3 positive, Si4 positive, Ti4 positive, Zr4 positive, Th4 positive, Pu4 positive, Bf3, Bcl3, Alcl3, AlH3, AlCH3, 3, Cl3 positive, Cl7 positive, If positive, I7 positive, RCO positive, CO2, Nc positive, HX. Soft acid: Cu2 positive, Ag positive, Au, Ti, Hg, Pt, Cd, Pt, Hg, Pt4 positive, Ti3 positive, BH3, GaCl3, GaBr3, Gi3, InCl3, I positive, Br positive, HO positive, RO positive, I2, Br2, ICN, OCl, BrIn, RO, RO2. Borderline acid: Fe2 positive, CO2 positive, Ni2 positive, Cu, Zn, Sb3, Bi3, NO, SO2, BCH3, GH3, RH3, IR3, RU, R3C positive, SN2 positive, Pb2 positive. Hard acids are cations of smaller size or lighter elements. Hard acids are cations of higher oxidation states. Hard acids are molecules, cations with lesser number of valence electrons. Hard acids hold the valence electrons tightly and consequently are not easily polarizable. In summary, hard acids bind strongly to a proton. Hard acids are small size, compact, are not easily polarized. A close look at 4.1 also revealed that soft acids possess the following. Soft acids are cations of large size or heavier elements. Soft acids are cations of lower charge. Soft acids are molecules with large number of valence electrons. Soft acids do not hold the valence electron tightly and are therefore easily polarizable. In summary, soft acids are large site easily polarizable ions, molecules that bind strongly to highly polarized ion molecule. It is important to note that there is no sharp division between hard and soft acids. There are a number of Lewis acids that are neither too hard nor too soft. Such type of acid that are neither hard nor soft are called borderline acids, which are shown in extreme right of table 4.1. Borderline acid have properties which are intermediate between that of hard and hard base, hard acid and hard base. In case of borderline acid, the properties such as the size, oxidation state, polarizability of cation molecule are neither too long nor high. On the other hand, soft acid will show the opposite trend, and the following order of preference for binding the donor atom ion with the group is observed: I negative, Br negative, Cl negative, F negative, R2Te, R2Se, R2S, R2O, R3Sb, R3As, R3P, R3N. The above 10 can be pictorially represented as weakest to strongest: R3N, R2O, F negative, R3P, R2S, Cl negative, R3S, R2Se, Br negative, R3Sb, R2Te, I negative. Weakest to strongest. What type of interaction do you expect between a hard acid and hard base? Since both hard acid and bases are not easily polarizable, these interactions are predominantly ionic. What type of interaction do you expect between a soft acid and soft base? Since both soft acid and soft base are usually polarizable, the interaction between them are predominantly covalent. Classification of bases. A general classification of some commonly used ligands, Lewis bases, into hard and soft bases along with borderline bases is presented in table 4.2. F negative, Cl negative, H minus, R minus, I minus, Br minus, NH3, RNH2, N2H4, C2H4, C6H6, C5H5, NC65H, C6H5, NO2, ROH, R2O, R2C, RO, RO negative, RSH, R2S, RS negative, N2, N3 negative, NO2 negative, H2O, OH negative, O2, 2 negative, Cn negative, SCn negative, S2O3, 2 negative, NO2 negative, SO3, 2 negative, SO4, 2 negative, PO4, 3 negative, CH3, CO negative, ClO4 negative, R3P, RO3P, R3S, CORN, NO3 negative. A glance at the table 4.2 reveals some of the important characteristics of hard bases. Hard bases bind strongly to the protons. Hard bases contain donor of high electronegativity. Donor atom in hard bases possess low polarizability. Hard bases are not easily oxidized. Hard bases contain empty orbital of high energy. In summary, hard bases bind strongly to a proton. The donor atom in case of hard bases is of high electronegativity and of low polarizability. A further inspection of table 4.2 reveals the following features. Soft bases contain no donor atom of low electronegativity. Soft bases contain atom of higher polarizability. Soft bases get highly oxidized. Soft bases are associated with the empty, low-lying energy orbital. In brief, soft bases contain electronegative metals, carbon, sulfur, phosphorus, iodine. The donor atom in such bases possess donor atom that are high, easily polarized. Just as there are borderline acid, there are borderline bases also. The property of borderline bases are in between those of soft and hard bases. It is important to note that the categories are not rigidly divided. For example, the halides form a series from the very hard fluoride ion through the hard borderline chloride ion to the borderline bromide ion, the soft iodide ion. The soft acid, also known as class B metal ions, are the group metal of metal ions that are in the lower right portion of the metallic atoms as shown in the figure. The classification of HSAB acid ion into hard, white, borderline, shaded and soft black. Pearson's HSAB principle. Pearson proposed a simple rule for predicating the stability of coordination compound formed between acid and bases. This rule is quite often named HSAB principle. According to Pearson HSAB principle, hard acids prefer to bond with hard bases while soft acids prefer to bond with soft bases. It is important to note that the hardness and softness of acid refer only to hard and soft interaction. It is by no means related to the strength of hard acids and bases. For example, both F negative and OH negative ions are hard bases, but strength of OH negative ion is 10 to the power 13 times that of F negative ion. In other words, hard acids will show the following order of preference of binding the donor atom ion which within a group: F negative Cl negative Bri, R2O, R2S, R2Se, R2T, R3N, R3P, R3S, R3Sb. Applications of HSAB principle. Pearson principle. HSAB has a number of applications in inorganic chemistry. Some of these are stability of the complex. We have already noted that hardness and softness of acids and metal bases are related only to hard and soft interaction. Hardness and softness of acids and bases has nothing to do with the inherent acidic and basic strength of acids and bases. For example, both OH negative and F negative ions are hard bases, although OH negative ion is for stronger base and F negative ion. In fact, OH negative is 10 raised to 13 times more stronger base than F negative. However, in HSAB principle, both OH and F negative ions are at par with each other. Pearson in 1963 explained the relative stability of coordination complexes on the base of HSAB principle. Let us consider a reaction between Lewis acid and Lewis base. A plus B, AB complex. Lewis acid, Lewis base gives complex. The AB complex will be more stable if E and B are either both hard or both soft. The complex A will be least stable if A is hard, B is soft, or A is soft or B is hard. For example, complex between soft acid and soft base is quite stable in contrast to one between soft acid and hard base. Ag positive soft acid, 2I negative soft base gives AgI2 negative stable complex soft interaction. Ag positive soft acid, 2F negative hard base, AgF2 negative unstable complex soft hard interaction. Similarly, the reaction between LiI and CSF resulting in the formation of LiF and CSI constitute an interesting example suggesting the preferential stability of soft and hard combinations. LiI plus CSF gives LiF plus CSI. Hard, soft, hard, soft. Some of the other important reactions suggesting the stability of the soft and hard interactions as given below. CuI2 plus CuF gives CuF2 plus CuI. CAS plus H2O, CaO, H2S, BeI2, HgF2, BeF2, HgI2. The rule of thumb in determining the stability of the complex is the preferential formation of hard and soft interaction. Why COF63 negative complex is more stable than COI63 negative. In both complexes, the oxidation state of cobalt is 3. But CO3 positive is a hard acid, therefore, in the combination with the hard base, F negative will lead to COF63 negative, which is a hard interaction. On the other hand, with the soft base I negative, it will lead to COI63 negative, which is a hard soft interaction. The COF63 negative is more stable than COI63 negative. It has also been noted that the combination of hard or soft ligand with a metal ion is always preferred over a combination of a mixture of hard and soft ligand with a metal ion. For example, the complexes COCN5I3 negative, CONH35F2 negative are far more stable, whereas the complex COCN5F3 negative and CONH35I3 positive are unstable. This is because Cn negative and I are both soft bases, whereas NH3F are both hard bases. Classification of acids and bases. The acids and bases can be classified as hard and soft depending upon their preferences for hard and soft reactions. BH positive plus CH3H positive gives CH3HgB positive plus H positive. We already know that H positive is a hard acid, whereas CH3H positive is a soft acid. If B happens to a hard base like NH3, the reaction on the left hand side will be preferred. NH4 positive plus CH3HG positive, CH3H positive, NH3 plus H positive. Conceptually, ammonium can be written as NH4 positive hard acid base, NH3 hard base plus H hard acid, which means the formation of NH4 positive is preferred because hard acid and hard base. On the other hand, if the B is soft base like R2S, the right hand side reaction will be favored as shown. R2HH positive plus CH3HG positive, CH3HG SR2 plus H positive. Conceptually, CH3HgR2 positive can be written as CH3HgRCr2 positive, soft equivalent to CH3Hg positive soft acid plus SR2 soft base, which means the formation of CH3HgSR2 is preferred because of soft acid and soft base. Similarly, an acid can be classified as hard or soft depending upon the direction of equilibrium. AF plus Cn negative ASCN plus F negative. We know that F negative is a hard base and SCN is a soft base. If A is a soft acid like Hg positive ion, then the above reaction in the forward reaction is favored. AgF plus SCN negative gives AgSCN plus F negative. Conceptually, as AgCN is formed through soft-soft interaction, hence according to HSAB theory, the reaction is preferred in the forward direction. On the other hand, if A happens to be hard, like Na positive, then the forward reaction is not favored rather than backward reaction is preferred. NaF plus SCN, NaCSCN plus F negative. Hard, soft, hard base gives soft and hard, hard. Conceptually, NaF is formed through hard interaction. Thus, according to HSAB, the reaction is preferred in backward reaction. OH negative is much stronger than SO32 negative and hence cannot be displaced by weaker base. This reaction, however, is favored by HSAB principle. CH3CDOH SO32 negative, CH3CDSO3 negative plus OH negative. It is important to include that the Lewis acid Lewis base reactions are governed by two independent principles: strength of the acid, softness and hardness of acid or base. The definition of hardness primarily uses the idea of polarizability, which states a less polarizable species is hard and a more easily polarized is soft. For ions of similar charges, the ratio of charge to radius should be used to assess the relative polarizability or relative hardness or softness. However, HSAB principle does not take into consideration the quantitative idea of relative hardness or softness. In summary, major limitations of HSAB principle are: HSAB principle is too general and without any qualitative scale of measurement. HSAB principle do not take into consideration the acidic or basic character of the compound. HSAB principle fails to explain the feasibility of the reaction CH3 positive plus H2 CH4 plus H positive delta H is equal to 86 kCl per mole. In spite of the soft interaction, it is probably greater acidity of protein relative to CH3 positive cation that is responsible for an unfavorable reaction. Limitations of HSAB principle: the hardness and softness of an acid or base is primarily related to the stability of hard and soft interaction. It has no concern with the acidity and basicity of the hard and of the acid or base. For example, OH and F are well known hard bases. However, basicity of hydroxide ions OH negative is very large as compared to fluoride ion. In fact, the basicity of hydroxide ion is 110 raised above 13 times of fluoride ion pK 2.85. A strong acid or strong base is well known to displace a weak acid or a weak base. For example, the reaction between a sulfite and hydrogen fluoride proceeds the forward direction and means the stronger base SO3 negative can be easily displaced with the weaker base. Form the acid SO3 into negative plus HF give HSO3 negative plus F negative. Our reaction is not favored according to HSAB principle detailed below. SO3 to negative plus HF gives HSO3 negative plus F negative, which only favors hard and soft interaction. Similarly, a very strong base can displace a weak base from soft acid and methyl mercury. OH negative, CH3Hg, SO3 negative, CH3HgOH, SO3 2 negative, K is equal to 10. However, the above reaction is not favored according to HSAB principle, which only favor hard or soft interaction. In both the above case, it is the inherent strength of base SO32 negative greater than F negative and OH negative greater than SO32 negative. It forces the reactions in the forward direction in spite of less preferred formation of hard soft pairs. This is true in cases especially when the inherent strengths of bases being compared to significantly different. The order of basic strength being OH negative, SO32 negative, F negative. In other words, significant different basic strength forces the reaction against the wishes of hard soft interaction. However, when both the strength of acid and bases and hardness softness are not significantly different, then HSAB principle work, resulting in the products having hard and soft combination. CH3HgF plus HSO32 negative gives CH3HgSO3 negative HF hard soft. CH3HgOH hard soft hard. It is important to mention the inherent strength of acid and bases should be ignored while applying HACCP principle. Symbiosis. The hardness or softness of an acidic or basic center is not an inherent property of an atom but depends upon the substituent. Thus, the ammonia is a hard base while pyridine is a borderline base. The acidic B3 positive is a borderline between a hard and soft acid. Addition of three small sized non-polarizable constituent like fluorine make it hard Lewis acid, whereas addition of electron donors and easily polarizable group like hydride ion make it soft Lewis acid. The difference in the hardness and softness of BH3 and BH3 can be illustrated nice in the following example: R2S BF3 R2O, R2O BF3 plus R2S, R2O BH3 plus R2S, R2S BH3 plus R2. Jorgensen observed that hard ligands have a tendency to combine a metal ion having hard ligand and soft acid having a tendency to combine with metal ion already having soft ligand. He coined the term symbiosis for such interaction. The hard BF3 molecule prefers to combine with hard base to form tetrafluoroborane, whereas soft acid in BS3 prefers to combine with soft base ion to give one tetrahydroborate ion. BF3 plus Fe negative, BF4 negative. BH3 plus H negative, BH4 negative, B2H6 plus 2H negative is 2BH4 negative. An important outcome of symbiosis is that symmetrical substituted compound are formed in preference to the unsymmetrical substituted compound. For example, the compound containing mixed substituents interact strongly to yield symmetrical compounds with the same substituent. BH3F negative plus BH3H negative, BH4 negative, BF4 negative, soft and hard. Similarly, mixed fluorinated methanes react to give symmetrical methanes. CH3F plus CF3H gives CH4 plus CF4. In brief, symbiosis may be defined as tendency of soft ligand to combine with metal ion already having soft ligands, and the tendency of the hard ligand to combine with the metal ion already having hard ligand. Theoretical basis of hardness and softness, HACCP principle. A number of theories has been proposed to explain the preference of hard acid toward hard bases. Electrostatic interaction theory. According to this theory, hard acid and hard base most form purely anionic compound. Hard interaction are purely anionic or electrostatic. Most of the hard acids such as Li positive, Na positive, K positive, hard bases such as O2 negative, F negative, OH negative are well known to form ionic compound. We know that electrostatic energy of an ion pair is inversely proportional to interatomic distance. It means the smaller are the ions, smaller will be the internuclear distance, and hence greater will be the electrostatic energy between the ions. As the result, the final compound formed by hard acid and hard base will be highly stable. Polarizing power and polarizability. Electrostatic interaction cannot explain the soft interaction because of the bigger size of soft ions. Therefore, the interactions between large sized acid and base must involve covalent character. For example, soft acids such as Ag positive, Hg positive, Cu positive form strong compounds with the bases S2 negative, I negative, which have substantial covalent character. Almost all the soft acid have 6 or more d electrons. Soft acid with d10 configuration are excellent. Soft acid in these d electrons that have more polarizing power. Secondly, the soft bases like S2I negative are easily polarizable. Thus, the bonding of between soft acid and soft bases is largely covalent. Natural occurrence of ores and minerals. The natural occurrence of ores and minerals can be easily explained on the basis of HACCP principle. Hard acids metal ions such as Mg2 positive, Ca2 positive, Al3 positive, Fe3 positive, Cr3 are frequently occur as oxide, fluorides, chlorides, and carbonate. This is primarily due to their preferred hard acid base interaction. We know that oxide, halide, or carbonates are all hard bases. These hard acid metals cannot occur as sulfide and S2 negative strong base and cannot form stable compound. On the other hand, soft metal ions such as U2 positive, Cd2 positive, Pd2 positive as occur invariably. They are sulfide due to soft acid base interaction that result in the formation of stable complex. Interestingly, the borderline acids such as CO2 positive and I2 positive Pb, Zn can occur both as sulfide as well as their oxide as a result of their intermediate character. Catalytic poisoning. All metal ions, metal atoms in zero oxidation are soft acids. Some of metal, namely V, chromium, nickel, palladium, platinum, molybdenum are well-known catalysts. These metal catalysts have been found to be easily poisoned by soft bases. CO, unsaturated hydrocarbon, olefins, alkyne, dienes, arenes, organophosphines, and organoarsines. The poisoning is attributed to the soft acid soft base interaction between the metal atom and ligand. In fact, these soft ligands are absorbed strongly on the surface of the metal and block the reaction and sites by forming the metal complex. In other words, the metal atoms lose their activity and are said to be poisoned. Thus, soft bases are complex with the metal in atomic state, which act as poisons toward metal catalyst. Electronegativity and hardness. Softness. Hard and softness are related to electronegative. Species with higher electronegative values are assigned greater hardness, with lower electronegative assigned greater softness. Electronegativity conventionally means the power of an atom in a molecule to attract electron towards itself. In this case, it refers to the power of an individual and participating in a reaction. For example, lithium atom is known as highly electropositive or low electronegative, but the cationic species with very high second ionization potential has a great tendency to attract electron. As a result, Li positive considered to be more electronegative, hence it is a hard acid. On the other hand, heavier transition metal is in low oxidation state like Cu positive, Hg positive, ACD positive have relatively low second ionization potential and consequently possess low value of electron. As a result, these ions are considered a soft acid. Using the same concept of electronegativity, we can define hard and soft bases. This relationship of hardness and electronegativity can explain several important features. Trifluoromethyl group is harder compared to methyl. Boron trifluoride is harder compared to borane. Ammonia is harder than trimethylamine. Trifluorophosphine is harder than phosphine, which is in turn harder than trimethylphosphine. Mulliken Jaffe defined electronegativity as a linear function of partial charge developed on an atom according as this Xi is equal to A plus B del. A is equal to negativity, B rate of change of electronegativity with the charge. Thank you.